Okay. So, hello to everyone. I'm Federico D'Ambrosio, and work to this project with E. Jung, Alissa Zaccaria, and Fabio Floreani. I'm a researcher from Intellimec. Intellimec is a consortium of 42 high-tech enterprises located in Lombardy region. And the consortium was established starting from the need to connect the industries, especially small and medium enterprises that are not able to perform internal research activity. So the consortium bring new technology in real environment and promote the innovation in the industrial ecosystem. Today I'm going to be talking about troubleshooting system, and in particular I'm going to be talking about troubleshooting system to support the detection of fault component in manufacturing industry. So to introduce the argument, I'm going to be talking about the troubleshooting. So the troubleshooting process consists in research activity that, based on symptoms, determine the reason of process malfunction. This activity is usually done by highly performant workforce and commonly trained on the job over a long period of time. And for this reason, normally for companies it's very difficult to substitute this employee and replace such a skilled workforce. And also the evolution of the machine complexity makes this process processively more tricky. In this context, becomes clear how computer-based troubleshooting system may present valuable support for the employee. This system has commonly training by starting from the knowledge collected by expert troubleshooting and can support less skilled employee that needs to be guiding through the identification of the fault component by asking questions related to the visible symptoms. However, troubleshooting systems are commonly based on a decision tree that makes the system unable to handle uncertainty. As we can see on the picture, a decision tree is a rigid logic which makes them unable to skip a question, because each node of the each node of the decision tree is a question that need to be asked and cannot be skipped. So one problem of this structure is that there is the possibility to get stuck if the operator don't answer to a question. And also another problem is that sometimes the time to arrive to the solution takes too much time or too much question, because the way the decision tree is made. So more flexible algorithm based on statistical rules may present a valuable alternative able to compensate for uncertainties and human errors. A similar approach is adopted by the popular game Akinator. For those who didn't know what Akinator is a game popular like 10 years ago. And Akinator is a game that simulates an artificial intelligence that can guess the character you're thinking, asking only 20 questions. Akinator is able to guess the character even if some of the answer provided by the player are wrong. And some features of Akinator are the possibility of answer in addition to yes and no to the other system. You can also answer I know, I don't know, probably not, or probably yes. And also an important feature is that you can skip the question. So as we said before, you cannot no longer get stuck if you don't know the answer to a specific question. And another thing is that the questions are not in a specific order, but are chosen randomly. And the game starts to asking common question at the start and ends up with a more specific question. So we tried to replicate the algorithm used in Akinator to apply it in an industrial context, starting from the creation of an appropriate matrix. As you can see, this is a knowledge base, is an information matrix as a knowledge base to a system, and on the left we have the fault, and on top we have the questions. And in this matrix, for each question, we have the right answer for each fault. If you want to use this matrix and improve it for a probability system, we need also to have the information about the wrong number that in this matrix is hidden. So for do this, whenever the answer right is yes, we will assign to the yes a value 0.9 and for the no a value 0.1. And whenever the answer right is no, we will assign the value 0.1 to yes and 0.9 to no. Now, so we can use this matrix to update the probability for each failure after each question. With this matrix, it's easy to understand that this system that with this system, none of the failure will be discarded. In the case of discrepancy between the information of the matrix and the answer, the probability of the failure will be decreased, but the failure will be no longer deleted. If you apply this to the matrix, what we have said to the matrix, we gain this type of matrix where we can see that we have both information of the right answer and the wrong answer for each failure. So the second key feature about the system is how the questions are sequentially selected automatically by the system. So normally in a decision tree system, the questions are chosen by a following pattern that it is already created. So if you answer yes to a specific part of the decision tree, you will get a specific question. If you answer no, you will get another one. But in a probability-based system, the order of the question is not predefined. So for each time the system identify, so each time the system needs to identify the best question based on the current fail probability. If I want to be more specific about this, because it's really important that you understand that the question chose is the one that approximately divided failure in two sides. So in this example, it will be the question number 4. But the weight of each side is not based on their current on the number of failure, but is based on the current probability of the failure. So it will be the sum of the probability of the failure that answer yes and of the failure that answer no. This is an example of the workflow, summarize of the workflow. So when the user starts the section, the system proposes a new question, And based on the answer, the system update the failure probability, as we showed before. And if one fault have a higher probability than the threshold, the system have found the right solution to the problem. But if it's not, it will identify the best questions based on the current probability, and it will again answer a new question to the operator. This cycle will be repeated until one fault is higher than the threshold. So we use this system and we test this system in a real industrial application related to a manufacturing company that produce and sell hydraulic cranes. However, the algorithm could be adapted to other different industrial contexts. In this case, the subject of investigation is quite complex. So to simplify the process, it is simple to break down the problem in simple sub-problems. Focus on specific block, and which is the user, and whenever he starts the troubleshooting, initially is asked to identify which block is the problem. So for each block we created, and we have a specific matrix of information. These are the results that we provide after the industrial case. So the system provides good result for us, being able to identify almost the 70% of the fault component, as we can see on the left. However, the system failed to identify the failure mode. With the initial information matrix, we know that slightly more than the 10% of the failure were correctly identified, and the 90% were not. So for this limitation, the initial matrix was extended, increasing the number of questions from 13 to 42 questions. And in this way, the system was able to correctly identify more than 40% of the failure modes, and significantly decreasing the failure modes that were provided highly uncertainty cases. Highly uncertainty cases are that failure modes that are not able to be distinguishable from more than 8 other failure modes. So this test demonstrates how increase the question to problem ratio leads to a better performance. Our conclusion is that the difficult part of this system is to create a nice matrix based on the question. On this case, we have a nice quantity of questions, so questions that decrease the uncertainty and prevent to end up with 2 or more failure that cannot be discriminated. But also is more important the quality of the question, because we need discriminating question. So question that divided the component into 2 groups homogeneous as much as possible, but also that are different between the other questions that are already been asked. And that's one things that we have multiple questions that divided the group in the same groups. So it's just a repetitive question that can be good if an operator wants to skip a question, but on the other hand, could lead to a multiple failure that cannot be distinguished. At this point, to improve the system, 2 things are needed. One thing is an expert operator who knows the system and is able to add question to the matrix and also able to test the system. And a second thing is an expert system. So an expert system that is able to self-learning and is also able to add new question or fault when the operator do not find the correct fault. So, this is an example of training for the system. So with an expert operator, if we found the fault, the operator will confirm the fault, and this will update the matrix probability. If the fault is not found, the operator is asked to add one fault, and also this means that this fault will be added to the matrix. And the last thing is that if you have multiple faults, as said before, we need to add a question to discriminate two or more faults that cannot be discriminated. And after adding a question, this will be added to the matrix. This is one example of possible improvement that we are working on. And in this improvement is involved the NLP, natural language processing, as means for communication between the system and the operator or the client in these cases. And for a simple scenario, this can lead to the answer. So only with the communication with the natural language processing, we can have the answer right. But if you apply this to a more complex scenario, the natural language processing can be a point of start. Then the system will start to ask the question. Thank you for your attention, and that's the end of my presentation.